Hello everyone, I'm Lin Fei from CVG in ETH Zurich, and today I'll present you our work called Camera Pose Estimation using Implicit Distortion Models. Given 2D 3D correspondences, we focus on estimating 6 degrees of freedom of camera pose. The camera intrinsics are usually modeled with a low-dimensional parametric model, but in this work, we aim at estimating camera pose without such model. Here, we make use of the radial alignment constraint as shown in this video. Points are constrained on these radial lines, and from here, we can estimate the camera pose up to forward translation. We can define a pointwise focal length f as the ratio between the image radii r and the distance of the pinhole projection point. Instead of describing it as a parametric function of the radius as in general case, we collect correspondences of each point to result in an RF mapping. Here, we show some examples of such mapping. They have differences. Some are curvier and some are flatter. Some might be non-negative and some can have negative values. But all such mappings share similarities that if the rotation and first two components of camera translation has been well estimated, with proper choice of forward translation, they should be smooth. You can see it clearly from the illustration below. Thus, we can estimate T3 by measuring the smoothness of the resulting mapping, and this gives an idea of our proposed regularization term. We formulate our problem into an optimization problem. We can decompose the reprojection error into two orthogonal components, one along the radial line and one orthogonal to the radial line. The orthogonal component is independent of the focal length and the radial distortion, but the tangential component is not constrained by the radial camera model, so we replace it with a regularization. Summing these two terms up would arrive at our proposed objective function as shown in this formula. The regularization is based on the local linearity assumption. First, we sort the image radii in ascending order. Then, we establish neighborhood for each point in a sorted list. We estimate the pointwise focal length by fitting linear function locally at each point. Then, note that each fi is a function of the 6 degree of freedom of camera pose. We proposed to use the distance between the estimated and the observed focal length as the regularizer, and we'll add a robust norm function on top of that to avoid problem of outliers. To evaluate our method, we mainly compare with Composico work in 2015, which is most similar to our method. Instead of the local linearity assumption, this work is based on non-decreasing property of the opening angle with respect to the image radii. We first perform some checkerboard calibration. For the pose estimation, our method outperforms the previous work in almost all experiments. Then, given the camera poses, we can recover an explicit calibration from the projection, and using this, we can evaluate the reprojection error on other images. When the estimated poses are used to recover an explicit distortion mapping by interpolation, we can see that we improve over previous method. Note that we obtain slightly worse reprojection error than the ground truth parametric model. Using the explicit interpolated distortion mapping, we can also undistort images. Note that these images were not used in the mapping estimation, showing that the calibration is not overfitting. We test the robustness of the method in the task of self-calibration in visual localization. On the challenging Aachen-Dana dataset, our method can achieve similar level of accuracy compared to jointly estimating a parametric model with a camera pose, and can even outperform it when multiple images are leveraged. It is also the similar case as in the Linlog dataset. Together with previous work, our method can achieve first truly calibration-free pipeline for camera pose estimation and reconstruction. To evaluate it, we use the 1D radial structure from motion pipeline to establish structure and motion. Since the estimation is only up to forward translation, we upgrade the result. We then apply the full bundle adjustment. Since our regularization introduces dependencies between 3D points, the short complement trick is not directly applicable, and we propose a simple heuristic to overcome this. We can see that the reprojection error generally improves compared with direct upgrading results, indicating the effectiveness of our method. For more details, please visit us in poster session 3.1 at 213A, and you can find code online. Thank you for listening.